Okay, we're going to talk about Introduction to ANOVA. Brief overview is going to be a discussion about the calculations, talk about the different parts of the ANOVA equation, then we'll go over a little output in SPSS and talk about the assumptions, which actually you guys should be pretty comfortable with already. I'm going to try to keep this short and sweet. So anyway, ANOVA stands for Analysis of Variance, and it looks really at a ratio of variances. This is a conceptual way to think of it. And it's really the variance that is attributed to group membership divided by the variance that is not explained. We're going to call the group membership between subject effects, and we're going to call the variance that is unexplained within subject variance. ANOVA extends t-tests beyond two groups because sometimes you want to look at not just men versus women, African American versus Caucasians. You want to compare multiple ethnicities, multiple programs of study, and so on. And ANOVA lets us look at all these comparisons with one single test, and I'm going to explain why that's important a little later on. And you can do this with between subjects designs, where I'm comparing different groups of people, or I can also do it with multiple time points and compare one group of people over time at several time points. So I could do it, an initial study, follow up a year later, look at them again another year later, and another year later, and I can try to tell if there's any difference in any one of those years rather than doing a bunch of t-tests that look at just individual pairs. So a simple example is like this. We look at some data. We have represented the differences that exist by looking at how people are different from the mean. I have talked about variance as just that, really just a way to quantify how people are different. And suppose that we have the following data on people's aggression on a 1 to 10 point scale. First, how many people total? How many people at each level? What is the mean aggression rating and why are people different? If I ask how many people total, well, I have 3 in this group, 3 in this group, and 3 in this group, so I have 9 people total. I have 3 different groups here, and I have an average aggression rating of 4. If I average everything out or I deconstruct these into their initial ratings, I get a rating, or I get an average rating of 4. Now the question that we have are, why are people different in this? So we're looking at Introduction to ANOVA, and I'm going to go over the basics of Way ANOVA, and I'm going to focus on the calculations, the equation, and what it all means, what it's actually doing. I'm also going to look at a little SPSS output. We'll look at this more in class. And then we'll talk about the assumptions, which are basically the assumptions that we already have. We've talked about these for t-tests, and so this should be nothing new. Now, ANOVA is an analysis of variance, and it looks at the ratio between the variance that is caused by group membership or individual differences that I can explain, and I compare that to the amount of variance that I have no idea why it's caused and I can't explain it. So you can think of it as a ratio of variance explained divided by variance that is unexplained. Variance due to group membership, variance that I have no idea why it's there. And the nice thing about ANOVA is that it extends t-tests beyond two groups. And you can use it when you want to compare 3 groups of people, 4 groups of people, 10 groups of people, and you just use one test. And I'm going to explain why this is important later on. And we're going to call it family-wise error. And it becomes a little more complicated than you would think it would be. But ultimately, the good news is that we just go back to t-tests to make different pairwise comparisons, and we're going to kind of limit the discussion to that for this class. Now you can use this when you want to compare changes over time as well as between groups of people. So when we looked at t-tests, we looked at independent measures t-tests, and we looked at paired sample t-tests, or repeated measures t-tests, same thing. And ANOVA can be applied in both those situations. It's just a bit more flexible than t-tests are. Now, a simple example involves looking at some data, and we have the following data on people's aggression on a 1 to 10 point scale. How many people total do we see? Well, we can count them up. I have 3 here, 3 here, and 3 here. I may wonder, how many people do I have at each level of aggression? Well, I have 3 people at this level, none here, 3 people here, none here, 3 people there. What's the average aggression rating for this group of people? Well, it's 4. And I may ask myself, well, why are these people different? It looks like I have maybe 3 groups, or maybe it's just everyone, and these values of 3 and 5 just aren't used that much. So ANOVA allows us to see if there are any differences between 2 or more populations of people, all in one simple test. Now, for example, suppose I'm wondering whether people with different eye colors possess different levels of aggression. We can test this hypothesis by gathering data about different people who have different eye colors, putting them into groups based on their eye color, and measuring their aggression in some way. Now, as usual, the null hypothesis says that there is no difference between these groups. And, in this case, it just says the mean of people with blue eyes, or I should say the mean aggression of people with blue eyes, is the same as the mean aggression of people with green eyes, is the same as the mean aggression of people with brown eyes. And suppose if we gathered data, we'd get this ultimate result here. And what I see when I look at this, you can't really see it on the screen, but I'll fix that in a minute. The blue-eyed people all have a value of aggression of 2. Everyone who has brown eyes has an aggression value of 4, and everyone with green eyes has an aggression level of 6. Now, when I think of the effect of eye color, I'm talking about how it makes someone different from the average person. So in other words, having blue eyes makes your aggression go down 2 points. Oh, typo on 2 there. And having green eyes makes your aggression increase by 2 points. So when I'm talking about the eye color effect in regard to aggression, I'm basically talking about how it makes people of that, or who have that quality, different from the mean. And because blue people, or people with blue eyes, are 2 points below the mean, I say it has a negative 2-point effect. Because green eyes seem to be related to a 2-point increase in aggression, I call that a positive 2-point effect. So talking about these effects of eye color, we look at 3 different things. We look at the total squared difference from the mean, just like we used to compute variance, the differences in the means of the different groups, and we weight these based on how many people we have in each group, which is important to do. And there's a couple different ways to do it, but we'll talk about that in class probably next time. And then the differences that exist within the groups. Looking at each group as though it were its own sample, and looking at the amount of variation that exists within the group of blue-eyed people, within the group of brown-eyed people, within the group of green-eyed people. And the idea here, how we used to talk about a ratio of observed difference to expected difference for t-tests and z-tests, here we're trying to say, well, what's the ratio really of the difference between the groups and the difference within the groups? And that's really what it comes down to when you look at the nuts and bolts of it all. Now, if we look at total variability, basically we're treating all 3 groups like they are a single sample. And I'm treating them in the way that I have traditionally computed variance for t-tests and so on, and I just take the overall average, which in this case is 4. I do my x minus the average, and here we're referring to the overall average as the grand mean, which is this capital M sub g. And then I'm going to square those values as well and come up with a sum of squares total. Okay, so I'm computing my sum of squares just like I always have. And the sum of squares just represents the sum total of the square differences of how people are different from the mean. Now, when we use ANOVA, we're going to be using this summary table that has 4 different columns and 3 different rows. First column is sum of squares, and there are between group sum of squares. In other words, the sum of square differences that are due to between group differences, the sum of squared differences that are due to within group differences, and the total sum of squares. The between sum of squares plus the within sum of squares equals the total. So total sum of squares, or total ways that people are different, are due to variation between groups and variation within groups. And that then, kind of accounts for all the variation that we're talking about. There's also a column for degrees of freedom, which we've talked about. In this case, they have slightly different values. We'll get there in a little bit. And then we have this mean square, which you can just think of as variance because that's what it is. When you think of variance and you think of how it's calculated, we do our sum of squares and we divide it by the number of observations we have minus 1 to get an average square difference or a mean square difference. And that's what MS, or mean square, stands for. The mean square difference or the average square difference, which is variance. And then we get our F ratio. And we'll see how this gets filled out as we go along. So the next thing we want to do is look at variability between the groups that we have. And in this case, our groups are based on eye color, and we have 3 of them. The first step is calculating the grand mean, which we've already done. Then for each group, we calculate the group mean. And when we look at this M sub k means the mean for each group minus the overall grand mean. So again, I'm calculating a sum of squares, right? I'm taking the mean of a particular group of blue-eyed people minus the overall mean. I'm squaring it. And then I'm also multiplying it by the number of people that are actually in that group. And when you have the same number of people in every group, it doesn't really matter that much, and you might be able to simplify things. But when you have unequal groups, well, those unequal groups actually impact the overall grand mean, and then the people, or the groups that have more people, are kind of given a little more weight in the overall grand scheme of things. So once we do all this, we basically apply that formula to each group. So for the blue people, I have 3 people times, parentheses, my mean of the blue-eyed people's aggression of 2 minus the overall mean of 4 squared. And if I do that, right, 2 minus 4 is negative 2 squared is 4. So I do this again with my brown-eyed group, and I subtract the mean of the overall group of scores from the brown-eyed aggression mean, which is 4 minus 4, because it's the same, equals 0, squared is 0, multiplied by 3 is 0, so that doesn't really add anything to my between group variation. And then I add the green people, or the green-eyed people, whose average aggression rating is 6, minus the overall mean of 4 is 2, squared is 4, times 3 is 12. So I have 12 plus 0 plus 12 equals 24. And when I go to add that into my between group sum of squares, I notice that my between and my total are the same, which means that my within group variation is 0. Now I can just fill in a 0, or I can double check, and I always recommend double checking because if you made a mistake somewhere, it'll mess up everything else. Draw the wrong conclusion. So I always calculate all 3 of them just to double check. Now, with sum of squares within, I compute the sum of squares for each group, treating them as their own thing. And I'm ignoring the overall mean here. It's just each x score minus the mean squared. And I add all those up, right? So I have my 2 minus 2, 2 minus 2, 2 minus 2. Square all those, add them up, that's 0. Same thing for this, same thing for this. And that's my total sum of squares is 0. Now, once I fill in the between group sum of squares and the within group sum of squares, I can move on to my degrees of freedom. Degrees of freedom are defined in this way, and this is something to write down, something to have handy. But the total number of people minus 1, or n, big N minus 1 in this case, we're using capital N to denote everybody among all groups, is my total number of degrees of freedom. Okay, so big N minus 1. Between groups' degrees of freedom is k minus 1, where k is my number of groups. And within groups' degrees of freedom are the number of people overall minus the number of group, or big N minus k. Now, as that works out in this case, right, I have 9 total people, 3 groups, 3 people. So my big N is 9, minus 1 is 8. My number of groups I have is 3, so 3 minus 1 is 2. And then the number of people I have minus the number of groups is 9 minus 3 gives me 6. I can fill those things in, and again, the between-within relationship stays the same. That if I look at my numbers, the between and the within should add up to my total. If they don't, I have done something wrong, and I need to figure out where that mistake has been made. Now, because you probably remember, of course, that variance is just sum of squares divided by degrees of freedom, I can get my variance by doing just that. This divided by this gives me this. This divided by this gives me this. And then I don't really divide anything here because I'm not interested in the total overall variance. I'm interested in the between group variance and the within group variance and the ratio that that gives me. Well, 24 divided by 12, or 20 by 2 is 12. 0 divided by 6 is 0. And then 12 divided by 0, which is my F ratio, again, my ratio of between group variance to within group variance, the variance I can explain to the variance I can't explain, is 12 divided by 0, and anything divided by 0 is really infinity, which is interesting. Now, if you're looking at how all this stuff fits together, this is a good slide to have handy. You have the equations here for each one. You have your degrees of freedom formula. You have your mean square formula, right? Sum of squares between divided by degrees of freedom between. Sum of squares within divided by degrees of freedom within. And then my F ratio is my overall mean square or variance between groups divided by my mean square or variance within groups. Now, we can go through Now, suppose we run this study again, and we get the following data. It's a little bit different, and if we look at it, there is some variation within each group. There's a little bit of difference in the blue eyes, and the brown eyes, and the green eyes. But if we look at the means, they have also changed, and we're going to have to determine whether or not there are any real differences in these groups. Now, if I look at my data here, I can see that my blue-eyed people have a mean of 2, right? They balance out. Brown-eyed people have a mean of 3. My green-eyed people have a mean of 4. If I calculate my sum of squares between, right, I'm going to look at, first of all, what my mean of each group is, and the overall mean. And in this case, the overall mean is 3 because everything's perfectly balanced, and that's nice and neat. But you could calculate it on your own if you want, or you could take my word for it. Trust me, it's 3. And if I go through that equation, I'm taking 2 minus 3, squaring it, multiplying it by 4, 3 minus 3, squaring it, multiplying it by 4, and 4 minus 3, squaring it, multiplying it by 4. Well, once again, that breaks down to 1 squared times 4 is 4 times 1. Plus 3 minus 3 squared is 0 times 4, which is 4 times 0, plus 4 times 1 squared, which is 1, which gives me 4 plus 0 plus 4, which equals 8. And I can fill that in right there. For within group variation, now I have to look at, this set of numbers in each sample a little bit differently again. My blue mean is 2. Well, if I do my squares or my sum of squares within each sample, or within each group, I have 1 minus 1, or 1 minus 2, I'm sorry, which is negative 1 squared is positive 1. 3 minus 2 squared is another 1, and so on. I get these values of 1, I get these values which sum up to 2, and I get these values which also sum up to 2. And when I add all these sum of squares together, 4 plus 2 plus 2, I get a total of 8. Sum of squares total is the same thing as we've always done. In this case, now I'm just doing each mean, or each x-score minus the overall grand mean, squaring it. These m's should be x's. Sorry about that. And I have 1 minus my grand mean of 3, which is negative 2. Square that, I get a 4. 3 minus my overall grand mean of 3 is 0. I square that, I get a 0, and so on. And I do this basically subtracting 3 from every single number, right? Squaring it, and then ultimately adding them all up. Now this gives me a sum of squares total of 16, which matches what I had before when I calculated my between and within. So again, between is basically measuring how different groups are different from the overall mean. And within group measures or of variance or sum of squares is looking at how people vary within each group. We fill in our degrees of freedom. We have 3 groups. K minus 1, which is K is our groups. 3 minus 1 is 2. We have, in this case, 12 people. And 12 minus 3, again, big N minus K is within group degrees of freedom. And then our total degrees of freedom are big N minus 1, which in this case is 11. If I divide across, 8 divided by 2 is 4. 8 divided by 9 is 0.889. And if I divide this by this, I get 4.5. And that is my F ratio. Again, my F ratio is a ratio of variances that can be explained by group differences. It's the variance that cannot be explained by group differences. And when we look at SPSS output, and in the basic sense, this is the ANOVA summary table that it gives us, and it matches the one that we have generated, pretty well. Just don't have the p-value. The p-value, of course, lets me know whether or not I say that there are statistically significant differences between the groups in here. It only lets me say that there's a difference in there somewhere, but does not let me specify where exactly that difference is. To do that, I need to do follow-up tests, but we'll get to those a little later. What I'd like you to do for this slide is just take some time and see if you can figure out what the missing values are. Now, I want you to understand how all these things are related to one another. And this is one way to kind of get practice at making sure those relationships are solidified in your head. Now, if I look at this first one, right, I know that this plus this equals this, but I only have one value and I really need 2. I also know that this divided by this equals this, which also means that this times this equals this. So, if I want to fill in my degrees of freedom here, it comes down to multiplying across and figuring out what times this equals this. In this case, 2 times 2 is 4, or I can just divide this 4 by this 2 and get the missing value. Now, that helps me out here, and from this I can fill out my total degrees of freedom, right? Being 12, 2 plus 10. but I still need to fill in this. And I know that this divided by this, my mean square between divided by my mean square within, gives me my f value of 2.5. So what I can do again there is divide this by this to get me this. So 2 divided by 2.5 gives me 0.80. Make sure that you understand, the differences between two ratios. If I have any particular ratio of 2.8 to 0.8, and that equals 2.5, if I'm missing the top, right, all I have to do is multiply this times this to get this. If I'm missing this, I divide this by this to get this. And if I'm missing this, I divide this by this to get that. And that's how it's all fits together. And if you're having trouble, remember that just make a simple ratio like 6 divided by 3 equals 2, and then just figure out what formula you need to use to get any particular missing value. Now once I have this, I know that this times this is going to give me this, just like mean square times degrees of freedom in the between row gives me between sum of squares. Mean square within times degrees of freedom within gives me my sum of squares within, which in this case is 8. I add those up, right? Oops. And I get a value of 12. And now I have filled in my table. And I'll let you fill in the rest yourself. The answers are there, just so you can see them. But it's important that you know how to do this because I will be asking you to do this on the exam. Yay! Now, the using SPSS portion, I'm going to go over in class more. I will just want you to pay special attention to this slide because this gives a label of everything. And if you want one to have handy about how to calculate anything or what anything means, this is a good one to have. As far as the assumptions go, we have normality, which you know what that is. It's just whether or not skewness and kurtosis are zero, basically, whether or not we have a symmetrical and an appropriately peaked distribution. We have homogeneity of variance, which, assumes that all the variances of each group are basically the same, and we've done that before. And then we have the independence assumption, which we talk about, again, just as making sure that no one person's values or scores influence another person's values or scores. And if you have questions on this stuff, let me know, but it should be review. We look at it basically the same way, right? I'm requesting my kurtosis and skewness, and I'm looking to see whether or not anything is above 1 or below -1 in each case. And if I look at this, skewness is great, everything's symmetrical, but kurtosis, in this case, I have problems all over the board, probably because I have this small sample. And so my normality in this case, because my sample is so much smaller than 30, would really tend to give me pause and make me question whether tests are actually valid. One thing that is nice about the homogeneity of variance test is that, like in an independent samples t-test, it gives me, if I request it, the Levene statistic, which is my little F ratio, that tests whether or not I do have variances that are different. Again, if my p-value is smaller than 0.05, I say that the variances are in fact different, and I need to do something differently. My regular ANOVA doesn't really matter. Now, with medium-sized samples or small samples, this is a problem. With really large samples, it becomes tough to quantify because Levene's test, like I said in class this past week, becomes very sensitive to small differences that are essentially meaningless if I have hundreds or thousands of people. Now, there are two options, basically, that I can choose if I do have a violation here. And it's the Brown and Forsyth and it's the Welch as my uh, statistical software allows me to kind of easily pick or ask for these two things. Uh, each one of them basically corrects for this inequality in variances. If you want to know more about it, I guess you can ask me, but I'm not going to spend a lot of time on it. I just want you to know that, like in an independent t-test, if I have a p-value less than 0.05 in my test of equal variances, that means I have to use the bottom row. This is the equivalent of the bottom row. And you have two options. You have the Brown and Forsyth, and you have the Welch. Now, the breakdown of how these things work is that under different circumstances, you have different strengths and weaknesses of each test. Now, equal sample sizes, when we talk about robust, that means that it gives accurate results. Conservative means that you fail to reject more than you should and you reduce power. When I say that it is slightly liberal, like in this case, well, that means that I'm having more type 1 errors than I really want, more false positives than I really want. So in this case, right, here's my F, my traditional ANOVA. Equal sample sizes. I have equal variances and unequal variances. For equal variances, I have an appropriate way to go. Unequal variances, it's robust, except I can inflate my type 1 error when the differences in variances are really large. And again, go with that 4-to-1 ratio. And so if the Levene test comes back as saying that the variances are different, actually look at the variances. And if the smallest variance is not 1/4 the size of the largest variance, well, then you don't really have a problem. Then regular ANOVA will be okay. When we have unequal sample sizes and we have equal variances, that's fine. It's just when we have unequal variances and unequal samples, and then we have different combinations. So when large samples are paired with large variances, then my F-test gets conservative, and I actually don't reject the null as much as I should, and I increase my type 2 errors. I reduce my power. If, on the other hand, my large samples are the ones with the small variances, well, now I'm going to underestimate the overall variance, and I'm going to assume, or I'm going to reject the null more often than I should, which is going to inflate my type 1 error. So these are the problems, really, where the regular ANOVA test breaks down in these two cases. In the other ones, it's really not that bad, unless I have really, really different variances. Just affects the probabilities. Now, the Brown-Forsyth is slightly conservative under kind of normal circumstances, but it can become slightly liberal when differences in sample sizes and variances are both very large. Or it can also become liberal when differences in sample sizes and variances are both very large in either one of these cases. Now, you don't want it to become liberal, and that's what you really are guarding against. Again, you have a robust test, except that it can become slightly liberal, again, slightly liberal, when you have certain conditions that are met. Now, what do I want you to know about this stuff? I want you to be aware that these are your options and that they are correcting for this inequality in variances. I want you to also know that neither one is perfect. The Brown-Forsyth is pretty robust when you have equal variances and unequal sample sizes, but that's not really what you're concerned about. You're concerned about when you have unequal samples. Unequal variances, and you're worried about these two cases here. And in both cases, each one test can become slightly liberal. And really, under they both become liberal under the same circumstances. And so the question is, which one do you pick? Well, you could do an analysis of which one is more beneficial, or you could just give you the one that gives you the more attractive result. And that's basically all I'm asking you to do in this class. Otherwise, we'd have to look at the equations, and the Welch equation is a real beast. We had to calculate it by hand when I was in graduate school, and it took forever. And it was very prone to errors and stuff, unless you set it up in Excel or something like that. But it was a long formula with a lot of like summation and whatnot across everything, and you had to do a separate calculation for the statistic and for the degrees of freedom and so on. And it's not worth it, and it's beyond the scope of this class. So you really want to maximize power, and that's going to be our main concern here. So you are just going to give or take the test, look at the results that give you the lower p-value. And in most cases, both tests will give you the same conclusion. It is rare, however, that one will give you be below that 0.05 point and one will be above. And again, it really then comes down to looking at the practical significance, looking at the effect size, looking at the Cohen's d, or the equivalent of Cohen's d, and r squared, and deciding whether or not this difference that you see or may not see, depending on whether or not you're above or below 0.05, is actually practically meaningful. And then finally, the independence assumption. Again, we already talked about it. Now, in class for next week, we're going to go over a few examples. We're going to look at the output. We're going to request a few things, and you can take the quizzes online to try to, test your mettle about what's going on in there, and try to make some decisions. Again, I will give full credit for all the points. If you just want to go through and see what the answers are and then try to figure things out, great. The important thing is that you spend the time with the material and really try to learn it. And that's it. Next up will be the two-way ANOVA